To understand and to predict motion, we first need to learn how to describe motion. So let's say we see some object in our surroundings whose motion attracts our interest. We know from experience that motion in the real world can be complicated, including perhaps shaking and rolling, spinning, twisting and turning. So to make any progress, we will pick out and study a single key feature of the total motion before we tackle other aspects. So here's how we'll start. Take the object that we're observing, and let's imagine in our mind's eye that we crush the object down to a point, placed at the average location of the original object. It's the motion of this point that we're going to focus on first. This average location has a special name. It's called the center of mass. Later, we'll learn how to calculate the center of mass for different objects. However, for now, if we use our intuition to pick a good point to represent the average location of the object, then that will be fine. The motion of this average location has a special name too. It's called translation. Now, even with our attention centered on the average location, the corresponding translational motion may be a little too complex for us to start with. So we're going to look first at cases where our object moves along a straight line. We'll call such cases one-dimensional or 1D motion. 1D motion happens in the real world, so it's useful to start here. We now will identify the physics concepts and quantities that we'll use to describe translation. Let's start with two concepts: the location, where the object is, and the time when it is at that location. To describe the object's location, or equivalently, the object's position for the 1D case, we can use a single Cartesian coordinate axis. Recall that we are free to choose the origin, orientation, and title of our axis, but once we make such a choice, we'll stick with it. For example, we are going to title the axis the x-axis, but we could have chosen any other name: the y-axis, the z-axis, the SpongeBob axis. The choice of label, as well as the choice of origin and of axis orientation, doesn't matter as long as we are consistent. So let's say when we first observe our object, the object's position is at x1, and the corresponding time is, say, t1. The position has the dimensions of length, and the time has the dimensions of time. We will often use the meter as the unit for position and the second as the unit for time. However, we will allow ourselves some flexibility here, as we'll try to choose units that are best suited for the situation we're studying. Motion often involves change. For example, let's say we see our object progress from x1 to x2 as time advances from t1 to t2. So we need to describe both a change in position and a change in time. The change in time is described by the difference, the final time t2 minus the initial time t1, which we can represent symbolically as delta t. The Greek letter delta is often used to symbolize a change. Notice that delta t, which is a scalar, will typically be positive because the final time is later than the initial time. Notice also delta t has the same dimensions and units as t1 and t2. The change in position is described by the difference, the final position x2 minus the initial position x1, which we can represent symbolically as delta x. The change in position has a special name. It's called the displacement. The displacement is a vector and therefore communicates two separate pieces of information: the direction of position change and the magnitude or size of the position change. Let's use an arrow to represent the displacement delta x. We do this by putting the tail of the arrow at the initial position, x1, and drawing the arrow so that the arrowhead lands on the final position, x2. Sometimes it's useful to draw the arrow a bit to one side for the sake of clarity. To help me remember how to draw the arrow correctly, I think of starting to draw the arrow at the start and finish drawing the arrow at the finish. By drawing arrows, we can see that a change in position from x1 to x2 is not the same as a change in position from x2 to x1. The two displacement vectors do not point in the same direction. Drawing arrows to represent vectors is a very good habit to develop. As a final note, we recognize delta x has the same dimensions and units as x1 and x2. Now, let's introduce a single concept that describes both how fast and in what direction an object is moving. Let's take the ratio of delta x to delta t. If we do that, we obtain a quantity we call the average velocity, Vx, where the bar over Vx symbolizes the average. The dimensions of the average velocity are length divided by time, with units typically meters divided by seconds, or meters per second. The average velocity is a vector which describes two distinct pieces of information: how fast the object is moving and in what direction the object is moving. Let's draw an arrow to represent the average velocity. Since the displacement vector is divided by a positive scalar to yield the average velocity, therefore the arrow we draw for the average velocity must point in the same direction as the arrow drawn for the displacement. The direction of both the displacement and the average velocity tell us the same thing, the direction of translation. However, the length of the arrow for the average velocity tells us something very different: how fast the object is moving. So, we have to make an extra decision about how long to draw the arrow to represent a particular magnitude of average velocity. Once we make that decision, we can then represent the average velocity for a fast object with a long arrow and for a slow object with a short arrow. Now, as an object moves, the object can speed up, slow down, or change direction. This can be captured by the change in the average velocity, which we'll call here delta Vx. We see that the change in average velocity has the same dimensions and units as the average velocity. To compute the change in average velocity, we need two average velocities. We computed one already, Vx1. Notice we added a subscript 1 because we're now keeping track of multiple velocities, and that this required a pair of positions and corresponding times. We need to measure at least one more position and time to obtain a new displacement and change in time so that we can compute another average velocity, Vx2. Then, the change in average velocity, delta Vx, will be given by the difference, the final average velocity, Vx2, minus the initial average velocity, Vx1. The change in average velocity is a vector, so let's represent it with an arrow. If we already have the arrows representing the velocities Vx1 and Vx2, then we can draw the arrow representing delta Vx. First, we start by putting the arrow tails for Vx1 and Vx2 at the same place, and then use the rule, start drawing the arrow at the start and finish drawing the arrow at the finish. This is the same procedure we applied a little earlier to draw the arrow representing the displacement, and is a general way to describe the subtraction of two vectors. As a vector, the change in average velocity carries two pieces of information: how much the velocity is changing and the direction in which the velocity is changing. We'll explore the meaning of the magnitude and direction of delta Vx later when we consider specific examples. So let's summarize. We now know how to describe motion, specifically how to describe the translation of a single object along a straight line. To do this, we need to say where the object is and when the object is at that location. We need to say how fast and in what direction the object is moving, which depends on our being able to characterize the object's change in position during a change in time. And finally, we need to say whether or not the object is speeding up or slowing down and or changing direction. The description of motion is called kinematics. The kinematic quantities we discussed here can provide a pretty complete description of 1D translation, but they're not sufficient for general understanding and prediction of 1D translation. Description is necessary, but not sufficient for understanding and prediction. So there's more to the motion story. We'll continue with that in our next segment.